Welcome to our discussion of extrusion additive manufacturing, which you may know as fused filament fabrication, FFF, or fused deposition modeling, FDM. Extrusion AM is arguably the most widely known and widely used of the AM processes that we'll study, and that's in part because more than 500,000 extrusion 3D printers are sold around the world every year. But it's not just applications in quick prototyping, but the use of extrusion for many important industrial uses. The classic picture of extrusion AM is that of a nozzle extruding molten plastic as it traces through the cross-section of a three-dimensional part, building it layer by layer until it's finished. And many 3D printers sold that use extrusion today actually process two materials, the first material being that of the part you're building, and the second material to build the support structures, which allows the support to be broken away or dissolved after printing is complete. Applications of extrusion AM range from small to large, simple to complex. For example, articles of personal fabrication, like this flexible bracelet, or complex housings, used in this case for prototyping of an electromechanical device. Extrusion AM is also used widely to make tooling, jigs and fixtures, and mold tooling. This piece of mold tooling is used in sand casting. The tool is 3D printed, and then sand is formed around its shape. And then the 3D printed piece is removed, and molten metal is poured into the sand form to produce this part. So the finished part matches the 3D printed tool with an offset due to its thickness. And next week we'll start to see industrial applications of AM, and one of those industrial applications is commercial aircraft. Many commercial aircraft have hundreds of 3D printed components made by extrusion, including duct work, and here's a small model of an aircraft duct component made by extrusion, and here's the as printed part. Here's the same part after surface finishing to reduce the surface roughness, and after coating by metal, which is another post-processing step that's possible using plastic additively manufactured components. The pioneer of extrusion AM is Scott Crump, who in 1988 had the basic idea and in his kitchen mixed up materials and prototyped a toy, a small frog for his 2-year-old daughter. That led him to automate the process using a 2D plotter and then a 3D piece of equipment in his garage, and he received a seminal patent for his idea, which covers the concept of three-dimensional extrusion of material from a moving nozzle. That led him and his wife to found the company Stratasys, and Stratasys shipped its first extrusion AM systems in 1992, and also trademarked the process named fused deposition modeling, FDM, which is still widely used today. The expiration of Scott's patent was also key to the growth of the industry. About 10 years ago, the RepRap project was founded in the UK, and this is a collaboration between engineers and scientists to enable broader use of extrusion 3D printing technology. And in this picture, you see two printers made by the RepRap project's open source approach, one called the parent and the other one called the child, because one of their core principles was to use 3D printing to make as many components of the printer as possible. And here it's mainly the plastic brackets you see around the corners of the frame. Now, Stratasys, the company funded by Scott Crump, has been one of the leading companies in the industry since its founding. It manufactures industrial additive manufacturing equipment for polymers and operates service bureaus that do production. And here you see Scott standing in one of the Stratasys service bureaus. In a very similar scene, we see here an array of industrial FDM printing systems and an animation of the process starting with the conveyance of the filament into the printhead, where the printhead builds a fan-shaped part, layer by layer, involving both the structure of the part and the support structure, printed at a lower density. When complete, the part is removed from the printer, separated from the build platform, and surface finished after the support is removed. For each AM process we study, I'll say we want to follow the material from raw feedstock to finished part. So for extrusion AM, using a desktop 3D printer like this, the feedstock is typically a thermoplastic filament, which comes in a spool and mounts to the back of the printer. Now in this printer, the filament is conveyed through these guide tubes to the printhead, which translates an X and Y in the planar orientation relative to the stage, which translates down in Z as the part is built. And we recently printed this bunny model, just like the bunny you saw in last week's introduction, where this is of course the part, and the second color represents the support structure. And having these two nozzles that move in tandem with only one of them printing at a time enables that multi-material print. If we look at two parts that were stopped prematurely, we can remember how now the trajectory of the printhead within each layer, defined by its toolpath, defines the infill from a solid, dense, stronger part to a lighter, less dense part with this sparse rectangular infill. Filament feedstocks for extrusion AM come in a variety of materials, sizes, and colors. Here's just a few examples. And this filament would be conveyed into this print head from the desktop 3D printer beside me through the top, where it's then heated to its melting temperature before it passes through the nozzle. And at the bottom of the nozzle it exits and it's laid into the part layer by layer. According to the label here, the nozzle diameter of this print head is 0.4 millimeters or 400 microns. Now in this printer, the heating mechanisms sit on the moving platform, going in X and Y, but the forcing mechanisms, what drives the filament forward and counteracts the viscosity at temperature, are attached to the frame. That's what's called a Bowden-style mechanism. Some industrial AM systems use filament as the feedstock, like smaller ones, and others use pellets increasingly as the feedstock, which is a lower cost way to provide a large volume of material and enable higher throughput printing. And also for each AM process we study, we'll want to examine parts in detail and use that examination to realize the limitations of the process compared to conventional manufacturing. So here we simply compare the look of an injection molded Lego brick to the same geometry made by desktop extrusion AM. And we see a big difference. The injection molded brick is smooth and shiny, and the 3D printed brick is pretty rough. There's layer lines on the sidewall, and there's the trace of the print head on the top. So overall the geometry is the same, but the quality is much different. And this quality influences the properties and the viability of the techniques for different applications when that really matters. Here under the camera I have 3 different gears printed using a desktop extrusion system. And they're the same geometry, the same part, but they're printed at different layer thickness. 200 microns, 100 micron, and 50 microns. And with the decreasing layer thickness, you can see the surface quality improves considerably. But there's a big trade-off in the print rate. The finer gear took 8 hours or so to print, and the coarsest gear took about 2 hours to print. And we'll also learn that pretty much every 3D printing process has a trade-off between speed and quality, or speed and accuracy. It's also important to recognize the connection between the process physics, the deformation and flow of the material in this case, and the part properties. In extrusion printing, you might think that the cross-section of each bead in each layer is circular because the plastic comes out of a circular nozzle. That's not true because the nozzle actually applies a force to the molten plastic as it traces through each layer, meaning that each road, as we say, is actually deformed, more like an oval. And this deformation is critical to the microstructure of the part. If you look at a cross-section of a failed part, one that's been pulled and broken, in a microscope you see how these oval cross-sections stack up both next to each other within layers and across the vertical span of multiple layers. And we'll talk later about how this influences the mechanics of extruded parts. And it's pretty much the case that extruded AM parts have a little bit of anisotropy. That means that the strength in the Z direction, if I define that as the direction perpendicular to the printed layers, is a little bit less than the strength in the XY direction, which is parallel to the layers. We're also seeing the application of extrusion AM to metals. Now how does that work? Well, one technique by a new startup called Desktop Metal involves first extrusion of a mixture of metal powder and a thermoplastic. That creates a first part that looks like this, and then has to be taken through 2 key post-processing steps to produce the final finished metal part. First, the 3D printed part is dipped in a liquid to dissolve some of the plastic, and then it's put in an oven at high temperature. Causes the metal powder to sinter together to form the final dense finished part, and that sintering happens very close to the melting temperature, but not quite at the melting temperature. The big difference you see here is not only in the color, plastic plus metal and finished metal, this is a steel alloy, but also in the size, because there's a lot of shrinkage, about 15% in each linear dimension as the part goes through the sintering process. And that's important to consider for accuracy, but can actually be quite repeatable and consistent. And as we like additive manufacturing for turning complexity into simplicity, this hinge was printed as a single component and has this single degree of freedom. Extrusion is also really exciting because it can span a huge range of length scales. Many research labs and companies are focusing on large-scale extrusion. For instance, Oak Ridge National Lab has a process called Big Area Additive Manufacturing, or BAM for short, which they've used to make large components of vehicles, dwellings, and even large wind turbine blade tooling like we saw briefly last week. And at the small scale, we can apply extrusion to making microstructures, not necessarily by extrusion of thermoplastic, because it would be difficult at that scale, but by taking fine nozzles and applying specially engineered ink materials through those nozzles. Applications of microscale extrusion AM, which we call direct write, include electronics, RF communication antennas, and many applications in bioengineering, such as building scaffolds for growth of tissues, and even depositing cells for applications in drug discovery.